again, we need to add some more definition, a couple of examples, and then we repeat that till end of this chapter and some other chapters. So we extend some of the definitions and we add some new definition. Two random processes are called orthogonal if you take any sample from x time t1 and any arbitrary time sample from the other one, if the two random variables are orthogonal. So if the dot product of these two guys, which is equal to this one, and you can write this is r x y of t1 and t2. If this cross correlation is 0 for all t1 and for all t2, then we call them orthogonal. That means that any sample from x is orthogonal to any sample from y. In that case, we say the two random processes are orthogonal. Remember that if you consider this as a random variable, it means that only at time t, if you take both samples at the same time, they are orthogonal. But in this definition, we mean that for all t1, arbitrary and arbitrary t2, they should be orthogonal. We say two random processes are uncorrelated if any two samples as two random variables are uncorrelated. That means that if you take a sample x at time t1 and y at time t2, these two random variables, the covariance of these shall be 0. So this is always equal to this one. So this is the definition, which is equal to mean of x of t1 minus mu x at time t1, the deviation from the center, and then y at time t1, t2 minus y mu y at time t2. We put a conjugate if they are complex. If not, that's okay to put a conjugate. And these shall be equal to 0. If they are equal to 0 for all these, we call them uncorrelated. So if I say x of t is uncorrelated v of t, it means that this is 0. If I say x of t are orthogonal to y of t, it means that this is 0 for t1 and t2 arbitrary. Now we want to have some new definitions, and you see that in this part we have lots of definitions and so on in order to simplify our communication with our colleagues and other researchers and so on. We call a random process A-dependent if you take any two samples at time, let's say t1 and time t2, as long as these two samples, if this distance is bigger than a, if the distance between the two samples is bigger than a, if they are independent. So if xt1 and xt2 are independent for large time separation, we call them correlation A-dependent if any two samples of x of t for large time differences is 0. So we call them correlation A-dependent if the correlation between x of t1 and x of t2 for the cases that the time difference between t1 and t2 is greater than a is 0. For instance, a speech signal for a equal greater than 50 milliseconds, they are correlation A-dependent. If you calculate any voice signal or music and so on, and if you take two samples apart more than 50 milliseconds, you see that they are uncorrelated. Or if you get a video of, let's say, a TV, and then if you take one sample from 1 pixel and then you take another sample 1 hour later, the image this hour and next hour, they don't have correlation. They are correlation A-dependent. Even more, I think that they are independent because they are coming from two different videos. So it is very easy to conclude that any A-dependent random process is also correlation A-dependent. It's very, very trivial. because any two independent random variable is also are also uncorrelated. Another definition, this is a very important definition, we call a random process wide if the random variables x at time t1 and t2 for any arbitrary t1 not equal to t2 are uncorrelated. In other words, if you reduce a to 0 for this one, you get white noise process. So if Cx x of t1, t2 is 0, we call it white random process. In other words, Cx x of t1 and t2 shall be equal to a delta Dirac function of t1 minus t2 times a function, and let's say q of t1. So this q is the power at time t1. A strictly white noise is the case that any two samples are independent. So this strictly white noise is a bit a stronger condition than the white noise. The white noise definition only involves the autocorrelation, but this involves them to be independent for all t1 and t2.